Everyone. My name is Aditya Nizap and I'm working as a product manager in the field of sourcing. So, working on this assignment, today we are going to look at how AI model or a machine learning model can be used to predict the electrical energy output of a combined cycle power plant, which is basically a combination of gas turbines, steam turbines, and heat recovery steam generators to generate power. As part of this project, we have been provided with 9,568 hourly average readings of different sensors which are installed in the power plant. These sensors capture the following factors, basically temperature, ambient pressure, relative humidity, exhaust vacuum, and depending on that, they have also provided us with the actual energy output which was obtained from that plant. Now, looking at the approach, we'll be using the regression model on Excel to determine or to predict the electrical output using the machine learning model. Let me quickly switch to the Excel spreadsheet. Talking about the model, we have broken down this project into four parts. The first part being modeling approach. So here our objective is clear that we have to estimate the electrical power output of the combined cycle power plant. And this is the reason why we will be using supervised learning model to train our machine learning model. Second part being model building. In this case, we are using a regression as the algorithm and considering factors like temperature, ambient pressure, relative humidity, and exhaust vacuum will be determining the electrical output of this power plant. For this purpose, we have split the data set, which is comprises of 9,568 uh, readings into different sets of 60, 20, and 20, being training set, validation set, and test sets respectively. The validation set here is fixed as we have a considerable amount of data to validate our model. Using the k-fold model here or k-fold validation method here will be extremely time consuming because we have a lot of readings available. Then for model evaluation, we'll be using or comparing the errors like mean absolute error and mean absolute percentage error. Here we are not using a mean square error as it heavily penalizes the errors which are uh, basically which are found in the model. For example, if one of the reading has a deviation of more than 5%, the system will heavily penalize this error, which could show that the model is not usable. However, there is a probability that such instances are very rare. So, to avoid that, we will be using MAE and MAPE. And in the end, for model interpretation, we'll compare the MAE and MAPE values for different models. When I say different models, I have considered the combination of different factors on the training set and validated it with the validation set to identify the errors, and the ones which least error will be considered for our final testing. Starting with the actual data, it will give me the regression readings on this training set. Okay, so just before the training set, I have obtained a new sheet, and here we have excluded ambient pressure, and temperature. So this is the same case which we saw here. We'll name it sample for now. What I'll do is I'll go to the validation set. I'll copy paste this entire information here. Now, using the readings obtained from the regression model, I'll create a new column, estimated energy output. And this formula would be intercept, I'm freezing this value, plus the coefficient for value, exhaust vacuum, my bad, which is multiplied by the exhaust value reading, and multiply the exhaust value into its coefficient plus relative humidity into its corresponding coefficient. This has given me an estimated energy output. Also find out the absolute error for this model, which is nothing but the difference between, let me take absolute value of the difference between the actual output and the estimated output. Also take a percentage error, which would be equal to absolute error divided by the actual energy output. We convert it to percentage. Sorry, I'll convert it to percentage. I'll also increase the decimals. Better identification or better analysis. I'll drag these formulas to the end of this training set, validation set. Now let me apply filter. Basically, I'm sorting the values on estimated energy output. We have energy output, which was the actual energy output recorded, and the estimated energy output. Let me also give you the formula for MAE, mean absolute error. Basically, I'm taking an average of this entire instance, and I'll also take mean absolute percentage error, which will be average of percentage errors. So here, if I look at it, let me validate it with my calculations. So this set and the sample set is giving the exact value. This is the sum of errors or the relative error. If I consider this model for my estimation, there is a chance of 1.4% error, or we can say that there is a possibility of an error of 6.4 units in the actual reading and the estimated reading. This is how I calculated the errors to validate or evaluate our model. Here, I've taken all the factors into consideration for my machine learning model, which gives me an estimated output with an MAE value. Let me zoom it a bit. With an MAE value of 3.697 and MAPE value of 0.815%. This is considering all the factors. The second one, I have excluded ambient pressure. So the formula for this will be the intercept plus coefficient of temperature multiplied by the reading of temperature. Similarly, exhaust vacuum and relative humidity. So this gives me an overall MA of 3.6968, or we can say that the MAPE value is 0.8153%. So if I note here, this model is giving me a better MAPE value as compared to this model. I've also taken multiple factors into consideration, like I excluded ambient pressure. Now I am excluding the exhaust vacuum. So this gives me an MAE value of 3.88, an MAPE value of 0.85%, which is greater than the first two models. If I consider a model excluding RH in the sense relative humidity, it is similar to the previous one. However, the MAPE value is still greater than the first two sets that we saw. If I am excluding temperature from my model, I see that there is a drastic change in the MAE value and MAPE value. It has increased a lot. This is not a what you call it. This is not an expectation that we have from the factors, and this is not something that we should follow. That is, in case our error is increasing by removing a particular factor, it means that that factor has some relevance to this model, and we should be including it instead of excluding this from the actual model. Here, I have excluded two of the factors, which are RH, relative humidity, and ambient pressure, which gave me an MAE value of 3.9 and MAP of 0.86 percentage. Here I've excluded ambient pressure and relative exhaust vacuum, which gives me MAE value and MAP value accordingly. However, we have seen that the first two models give us the best MAE and MAP value. And after removing temperature, after excluding temperature as factor from our model, these errors keep on increasing. So to ensure that we consider all the cases, I have also run a model on only temperature as the relevant factor. However, it still gives me an error of 0.94 percentage. So which means that considering all the factors or just excluding the ambient pressure, I'm getting a better conversions to the uh, actually recorded energy results. So what I've done is, since the first two factors here, first two models, considering all the features, and the second one, which is basically using temperature, exhaust vacuum, and relative humidity. The MAE value here is 3.697, MAP value is 0.815, and here the MAE value is 3.6968, which is equivalent or approximately equal to 3.7, 3, yes, 3.690 0.7, an MAP value of 0.815%. Since these two are relatively similar to each other, I've ran the test set, or I've ran the results on test sets for those two models, and I've observed that the MAE value, considering all the features, is 3.66, or the MAP value is 0.8084. Whereas if I exclude ambient pressure, this value, MAE value, here it is 3.66029. It increases a bit by 0.001, and the MAP value increases by 0.0016. Considering those two models, I would say that all the features which are provided by the sample data are relevant for our machine learning model, and it will give us the best result. So talking about summarization of this AI machine learning model, we can say that all features are relevant for estimating the energy output for the combined cycle power plant, and we have concluded that on the basis of MAP value, which gives us a better interpretation in terms of relative comparison between different models. Thank you. That was it for today's session, which was uh, predicting the electrical energy output of a combined cycle power plant consisting of gas turbines, steam turbines, and heat recovery steam generators, using a sample set of features including temperature, ambient pressure, relative humidity, and exhaust vacuum.